few introductory remarks. Until yesterday, the people who were working on the co-lecture series didn't really know if anyone would be interested, or even if the idea of a public lecture series was worthwhile. You know, once you get into something, you just keep doing it until it's done. But I think after yesterday and Don's, I think it's an exaggeration to call it a gripping talk that gave an inside look at how mathematician grapples with important problems. I think we realize the co-lecture series now feels like an established thing, and now it's no longer something we're trying to do. It's a responsibility to live up to try and meet this standard year after year. So thank you for that. So I won't repeat what was said about Don yesterday, but I will say he first visited here, I think, around 1980 because he was a fan of Tony Danby's work. Tony Danby was a mathematical astronomer in this department. Since then, one's been able to keep up with Don just by listening to NPR on the way home. I heard him once being interviewed about the Unabomber, who apparently approached Don once to try and get a paper on the dangers of technology published. Another time I heard him interviewed about voting methods, which he spoke about here at the Scope Academy a couple of years ago. Since 2000, Don's been the director of the Institute for Mathematical Behavioral Sciences at UC Irvine, which kind of passed by yesterday. It's a unique place, as far as I know, that fosters the use of math modeling in the social sciences. I figured Don had started it, but it actually goes back to 1989. It was started by Duncan Luce, who's one of the fathers of modern mathematical psychology. He was awarded the National Medal for Science in 2003. I actually attended a wonderful conference there in January about the evolution of religious and social norms, where you could hear social scientists who bought into this idea that they need to make mathematical models, which forces them to express themselves much more clearly than the social science I remember from college. Really completely fascinating experience. So anyway, today Don will talk about using symmetry groups to understand puzzles with social sciences.
Thank you. I guess I have to say one word about. I haven't heard the word Unabomber in a long time. But my buddy, Ted Kaczynski, in fact he was, what he did is he would come over and gab with me for a long time on a weekly basis or something like that. So I got to know him fairly well. And as a result, yeah, I became very close contact with the FBI on a daily basis, everything else. And I also introduced him once when he was in 1977 to a large number of mathematicians. 15 years later, or I don't know, in 1995, all of them received visits at Northwestern University from the FBI. Wondering why me? But hey, look. But it was an interesting story. But I want to talk about something different today. I want to talk about using mathematical symmetries to explain some social science puzzles. And really what I want to talk about, and if you heard me yesterday, you know what is my theme already. My theme is really to promote mathematics, but to try to push it in other areas in the following ways, is that indeed, mathematics plays an important role in understanding computations and solving the various problems and puzzles that come up in the various different disciplines in the world. But I really think that it has something even more important. That mathematics plays a huge role in creating conceptual breakthroughs in these areas. And that's what we as mathematicians should start, remembering that and promoting it in various areas, because we can have a huge impact. Now, what happens is, most of my earlier work was in mathematical astronomy, and recently it's been in engineering. Now let's look at the history of this. Let's look at the history. Mathematics and the physical sciences. We've had a 2 millennia symbiotic relationship. What happens is the physical sciences make a breakthrough. And then mathematicians come along and say, aha, here's what's going on, and here's why it's important, and here's how you can advance what we knew about it. And then this allows us to go another step forward, and so the physical scientists say, oh, we can make another breakthrough. And that's been going on for a couple of millennia. What that has done is it has significantly shaped the physical sciences, and it's also shaped mathematics. Because a lot of the mathematics we do today is mathematics generated, motivated, inspired by the physical sciences. And that's going to play a big role in what I have to say today. Because now I'm a so-called economist, and I also work in behavioral sciences. Is it possible, and this is my wish, is it possible to create a similar symbiotic relationship between the social and behavioral sciences and mathematics? I mean, let's face it, the social sciences are behind. And why are they behind? I think that if they can have a stronger mathematical type connection, it will make serious advances. So I'm trying to throw out a challenge to everybody in this room. Now, the mathematics has to differ from the social sciences. Let me explain why. Walking over for lunch today, I found a penny. We'll use that. In the year 1859, let's take a look and see the difference between the social sciences and the physical sciences. In the year 1859, a mathematician took the Newtonian Equations of motion. Now, let's see what happened. Suppose we had a universe that consisted of the sun and the planet Mercury, nothing else. No Earth, no moons, no Jupiter, nothing else. Then Mercury would go in a perfect ellipse about the sun forever. But we have other planets out there. The sun, we've got Venus, we've got Saturn, Mars, we've got all of them. And they pull that, they change that shape of that ellipse. They keep moving that ellipse around. So now perihelion is the closest approach. Now, what happens is, in 1859, they wanted to make predictions. What are the predictions based on Newtonian equations? Newton's equations of motion. And they determined how that perihelion should be changing versus observations. And they found they were off by 43 seconds of arc per century. What is 43 seconds of arc? See that? See that? I got 2 coins in mine. See the thickness of that? In the back room, Steve might have a little trouble seeing this. What about if I stood on the other side of a football field? That's 43 seconds of arc. And they were off that amount per century. And it created a crisis in whether we should believe in the Newtonian n-body problem or not. It turned out the crisis was a correct one. It took Einstein's general relativity to explain that big difference. But now let's go to August 2008. The most mathematical of the social sciences is economics. How many economists, professional economists, do you think there were that were within 10% of what was going to happen not a century from now, but next month? A couple were bragging, well, we knew something was coming about. But nobody predicted when, nobody predicted how far. The precision of the physical sciences and the social sciences are off. And in fact, that makes a very, very big difference. And the social sciences, what is it that we're interested in? We are not at the stage yet where we can start looking at quantitative, how precise that is. We are at the stage where we want to create mathematical tools to understand qualitatively what's happening. What can I predict? Qualitative is about the best we can do at this stage. And that's all why math has to differ. It has to match. It has to not try to solve problems, but mathematics has to come to the conceptual idea. What are the conceptual type mathematical tools that will help on conceptual breakthroughs? That's our challenge. So in other words, these equations here, x dot equals f of x, that we're used to writing down, These were sharpened by experiments, sliding things down planes, by observing satellites, by everything else. We know what f of x is. And yet in the social sciences, they write down x dot equals f of x, and they have no idea what f of x is. None whatsoever. F of x is behavior, and that's what we're trying to understand. So there are so many challenges. How can we talk about dynamics without knowing what f of x is? I have a different lecture on that, but I'll just leave that as a challenge. And so what can be done? And I'm going to try to outline the change. I'm going to try to give you a flavor of ways to try to get some answers, just to give you a flavor. And really, I'm putting forth a challenge to all of you. I want you to look at these type of problems and say, yeah, I can make a contribution in that direction. But remember the differences of the social sciences from the physical sciences. If you can see the qualitative difference between them, that's necessary before you can start making contributions. Now, let me give you some examples. And for this example right here, first example, see, I'm a director of a research institute. So I go to all the colloquia. And a lot of them, I have no idea what the world I'm talking about. Well, that's true when I go to math colloquia sometimes too. But I have no idea what they're talking about. And so what happens then is, but I listen to them and I learn a lot, and I discover that a lot of them are about fascinating experiments. Now watch closely because I'm going to give you a quiz. It's going to flash up here. What did you see? What did you see?
A lady.
And what was her, what was she? Happy, sad, crying?
Couldn't really tell.
Yeah.
I think she was showing disgust.
Disgust?
Maybe.
Okay, let's try that again. Watch closely. I'm going to give you a quiz. Oops. I went too far. Ha! I see. I pushed the wrong button. Okay. Modern technology is full of buttons that you have to be careful about. All right, so let's. Okay, here we come. What was your emotion?
Kind of like a smirk.
Smirk?
Yeah, it was kind of, one side was up and one was down.
Lopsided face.
Well, yeah, but you know. That's no fair. When I heard you were coming, I was going to say, yeah, avoid Nancy. Okay. You're right. It's a Photoshop type thing. Where what we have is if you lock it off with your eyes, you see one side, you know, there's one emotion, and the other side, there's a very different emotion. And there's a lot of experiments on these things, aren't there? Trying to understand what's going on. Now, what are some of the experiments which we have? Why is it that we see one side of the face? Most people see one side, not the whole face, except for you. Why is it that we see only one side, not the whole face? And the question is that there are many, many experiments with this, with different emotions. And they tend to be reasonably consistent in terms of which side of the face you see. And so the question then is that we have to remember that experiments by nature are local in nature, you know, just by how they're designed. I find out what's happening here. And so the question that I raised after looking at these and talking to my psychologist friends is that, is it possible to have a global picture? Can mathematics be used to get a global picture of what's happening? And indeed, I'm going to show you how to get this. But the important thing I'm going to ask is also, will the global picture help provide an answer to the question of why we usually see only one side or the other? Okay? So is there a mathematical explanation why we see one side or not the other, but not that? Now you see, well, we got two sides of a brain. The answer is obvious. So I have to read it in Anatomy 101 or whatever it is. And the answer is, well, can I construct a brain? Would it be possible to construct a brain where you would have this type of behavior? So we will come to answers for some of these questions as we move along. Here's another one. It's called Centersurround. Now, this isn't a very good picture, but the experiments are that I have a center, a color, and I have a surround. Now, as I change this color right here, your mind is going to change that color. That color doesn't change. As I change this color right here, your mind is changing that color right there. Why is that? What's going on here? And in fact, you might say that it's evolutionary necessary. Here are some of the experiments and some of the explanations they give for evolutionary type problems. I'm an animal. I'm going around looking for a red apple. I'm in color bias. The color is going to tell me whether to go for this fruit or not. And then all of a sudden comes a fog or something, or changes the background color. And I still see that same color. So that's part of the color surround when the color has changed, but in fact, I see it as the same color. It's a different version, but it's the same thing. And so the question that we have then, or the Centersurround, is why does one feature dominate? And there are situations where they take turns which one dominates. And there are many, many papers, many experiments. And again, just by reality, the experiments define the local structure. What's happening locally at this situation, that situation. And so what we want to know is, can mathematics provide a global? What kind of mathematics would we create to get a global picture? Right? And find an answer. Another example. Any questions on what I have so far? Any criticisms, disagreements? Okay. Another example. The size of the House of Representatives. Every 10 years we change how many representatives come from the state. What happened to North Carolina? Did you gain one or lose one? You lost one?
No, gained one.
Gained one, okay. California, I think we lost one. Doesn't matter, we still have the most by far. But the question then is, the size of the House of Representatives, at one time, the size of the House of Representatives changed. And I'm talking about 1870. In 1870, with the census, so in other words, if your state right here has 1/3 of the population, you should have 1/3 of the representatives. All right, 1/3 of 16 is 5 and, all right, we'll saw off part of that representative or something like that. But, so we have a question of rounding off and things like this. But the Alabama's had 7 when the House size was 299. And so they said, I wonder who would get the extra state if we moved it up to 300. And what happened is, Alabama lost. There's more to spread around, and Alabama ended up losing a state of representatives. They had 7 when the House size was 277. They still had the same fraction of the total population for the United States, and yet when the population went up, they ended up losing. This is just an example of an allocation problem. In the social sciences, we have allocation problems according to fairness, whatever that means. And so allocation problems are everywhere. And what happens is this type of phenomenon arises consistently. And the question is why? Here's one. Anyone here, don't give the answer if you do know, but anyone here know why we have 435 representatives? Anyone here know why we have 435 representatives in the House of Representatives? I'll give you the answer later on, but I'll tell you right now, it's mathematics. Strictly mathematics and symmetry type behaviors. Do math symmetries play a role? I already told you, they do. Okay? They don't play a role in this. Now what we do is, so I've given you some of the problems, so now I'm going to start giving you a problem and showing you where symmetries crop up, and then I'm going to answer all of the first several questions that I raised. The first question, the question I'm going to talk now, are decision problems. I was talking to some of the graduate students, and I understand they're going out and having a party after my talk. Now, as we all know, graduate students have no money. That is a given, okay? And so therefore, they're going to have one beverage. 6 of them prefer milk. Weren't you the one? That line was here. 5 prefer beer and wine and milk. And then 4, they're from California. They prefer wine. Now, you can afford only one beverage, and so what are you going to get? There, you're going to vote. And you vote. 6 people vote for milk, 5 for beer, 4 for wine. Folks, we're in for a called a milk ceremony. Milk wins by beer, wine by the vote of 6 to 5. Okay, no big deal. I mean, let's take a look. And in fact, that's quite fair. Let's take a look at milk and wine. Milk, wine, wine, milk, wine, milk. Something wrong here. Because what happens is 60% of these people really prefer last place wine to first place milk. And 2/3 of them would prefer last place wine to second place beer. So wine was in last place. Remember, this is the election method which you're using in your elections. Remember, that you used in your primaries here. The plurality vote, and what you use to select a department chair. Or are you, or are you a dictator? I see, good. And everything else. At the look, we have this outcome, and last place wine is really preferred over all the other alternatives. And let's take a look at first place. Beer, milk. Beer, milk. Beer, milk. 60% milk came in first. And by landslide proportions, they don't like milk, and neither do I. So what happens then is the outcome is exactly the opposite. It's exactly opposite. Milk, beer, wine. Here we see wine, beer, milk. Exactly the opposite. And folks, I'm talking about the decision procedure that we use every year, every election year, and within departments, and we decide what pizza to order, and everything else. And so the problem then is that the social sciences, which is a central issue in all of the social sciences, it's a central issue in engineering, it's a social issue in statistics, and on. It is to decide. And as this example shows, that answer can depend on what method you're using rather than the data. The winner of an election can depend more on what election procedure we are using rather than what the people want. And so the problem then is what method should be used to get legitimate outcomes. Now, I'm not going to go deep into here. I just want to use this as a way to show where symmetry crops up. It's a problem that's about 250 years old. And the problem was discovered by a French mathematician, Jean-Charles Apportion, partial differential equations. He objected to who was being elected into the French Academy of Sciences, and they were using this method right here, and he said, that's stupid. And so what he did is he said that if you have 3 candidates, you should give 2 points to your first place candidate, 1 to your second, and 0 to your last. Okay. And Condorcet didn't like Borda, and they had a fight. Condorcet said, we should use pairwise. Is what we should do. But now, this problem's been around for a couple of centuries, and we're finally getting answers of how to do this. And where do they come from? One of my themes today, symmetry. One of my themes is that symmetry and algebraic topology are tools that will help give us insight into a lot of the problems in the social sciences. Now let's take a look at the symmetries. Well, let's look at something simple. Suppose I have 5 people. Well, it's pretty clear here what the people want, don't they? Wine, beer, milk. However, somebody else cares about that person. Okay? So wine, beer, milk is the outcome. And let's look at another example, a different example. Well, this person believes this, and this person believes the opposite, so they cancel. So we should get a tie here. See, if I have milk wine, I get wine milk. If I have milk beer, I have beer milk. I mean, just the opposite, so I should be a tie. And what happens then is, so here I have something where the outcome is known. Here I have something that should be a tie. We add the two together, and what do I get? My original example. Now, how does this handle? Suppose we vote for one. What happens if we vote for one? If we vote for one, milk gets 5 votes, beer gets 5 votes. We don't get a tie. Because what happens is wine gets no votes. Suppose we vote for two. Milk gets 5 votes, wine gets 5 votes, beer gets 5 votes, wine gets 5 votes. Wine wins now, just reversed. Wine's now the winner. So what I have, in mathematical terms, is I have a Z2 orbit, a group orbit. Flip and identity. Reversal and identity. And this orbit of preferences has no effect whatsoever on pair comparisons, on the pairwise vote. But it changes all of the methods, like the plurality vote, or vote for two, or 6 points to the first place candidate, 4 points to the second place candidate, etc. So it turns out that the simple argument I just gave you right here is really the source and explains the 2.5 centuries worth of papers, thousands of papers, about why we get paradoxes and everything else. Just the Z2 symmetry. This and its reversal. If I got those components in a profile, you're going to have troubles. Let's get another example. You know it's very tough in California. So what I do is I have a consulting firm. For a price, I'll come to your organization before your next election. You tell me who you want to win. I will design a fair voting system so your candidate will win. Okay? And so here's going to come another symmetry. The example is where I have 10 people preferring Anne, Barb, Connie, Deanna, Elaine, Fred. 10 people preferring Barbara, Connie, Deanna, Elaine, Fred. And 10 people, Connie, Deanna, Elaine, Fred. Everybody prefers Connie to Deanna to Elaine to Fred. So let me show you how to elect Fred. With a very fair method that's used in all departmental meetings. Okay. And it is nothing more than an agenda. You have an agenda, Robert's Rules of Order. You have an agenda. And so what you do is I'm going to have Deanna versus Elaine, and the winner's going against Connie versus Barb versus Anne versus Fred. Well, I already told you here that everyone prefers Deanna to Elaine. And Deanna versus Connie, everyone prefers Connie. And Connie versus Barb, 10. 2/3 of them prefer Barb over Connie. And Barb over Anne, Anne. 2/3 prefer Anne over Barb. And Anne over Fred, 2/3 prefer Fred. When I show this example to engineers, they have a fit. Why? They use paired comparisons to make decisions. And they say, you mean we could be making the wrong answer? And the answer is, you better believe you can, and the likelihood of that happening is high. And in psychology, and that you know, they use paired comparisons all over the place. And they use the data in this way. And the question is will you have the right answer? Probably not. I mean, look at the data. You have strong validation, verification of the way it's incorrectly used in the literature. Because the data is unanimous. 5 and 2/3, 2/3, 2/3, 2/3. The data says, boy, this is clearly the correct answer. And it's not. So the challenge is to try to find out what goes wrong. And so let's see what goes wrong. What goes wrong is another symmetry. I bring in what I call a ranking wheel. Come on, ranking wheel, come on in. There it comes in, kind of slow. It's getting a little old. Okay? And so I'm going to put ranking numbers. There's 6 candidates, so I put numbers 1, 2, 3, 4, 5, 6 around it. And then I'm going to put the names of the candidates. Anne, Bart, Connie, Deanna, Elaine, Fred. Anne's in first place, Bart's in second, Connie's in third, Deanna, etc. And so I have that ranking, which is the one we have here. Now what am I going to do is I'm going to rotate this 60 degrees. And so now I have Bart's in first place, Connie's in second, Deanna, Elaine, Fred, Anne. You see what I'm going to do? I'm going to continue rotating it. Okay? Okay? And now I'm going to get here. But I'm going to continue all the way through. Now, by construction, what's happening? Each candidate is in first place once. Each candidate is in second place once. Each candidate is in each place once. Okay? So there's no difference between the candidates. It should be a tie. And what is this? That if you use weighted, like plurality vote, etc., it will be a tie. But pairwise elections will not be. There'll be a cycle. And that's because of lost information. Let's look at BC. B is better than C, B is better than C. Uh-oh. Here I have that C is better than B, but then C is going to drop down, and B will be better than C all the way down the line. We're at this symmetry. It's a symmetry, right? We're at this symmetry. What do we have? We have an outcome that should be a tie, and yet it's a cycle 5 to 1. A beats B 5 to 1, B beats C 5 to 1, C beats D, D beats E, E beats F, F beats A. All the way around. Jean Lieber would love that cycle. Okay? And so what we do is we have this information. And what's the point? The point here is that I have a symmetry group. It's a Z6 orbit. And the theorem is that Z, if you have n candidates, then the Zn is the source of all cycles. Whether they come in voting, social choice, statistics, psychology, engineering, whatever area. So that this is the symmetry group right here that causes those mysteries that have been around for centuries. And it's a total explanation. The theorem is if and only these cause problems. Nothing else. So what have we done? I've taken a decision problem now, and I've shown that with a decision problem, all of the difficulties you have are caused by symmetry groups, and this goes for any number of candidates. And so exactly for 3 candidates now, it says that all possible problems, all possible difficulties, all possible anything, this 2nd-century literature, can be understood just for Z2, take a ranking and flip it, you know, that there, or Z3, just rotating. And that all possible difficulties that have been in the literature are special cases. This is what I'm saying. The role of mathematicians is to look at some of these issues and to try to extract what are the conceptual issues and problems that are causing these difficulties to occur. That once we do that, now we're going to be able to change the field. Because the field no longer has to find any more paradoxes. They know why all paradoxes crop up, etc. In fact, to analyze it, what these do is they create a coordinate system, so linear algebra can be used now to handle what were previously difficult problems. Any questions on this? Because I'm going to leave this behind. Okay. Party. Time for a picnic. We're going to go to a beach. We're going to have a picnic. Okay? And so therefore it's a beach. I just am interested in the beach. Now, question. 2 people are going to the beach, Bob and Sue. So what do? Sue has one choice, Bob has another choice. And the problem is to choose where are they going to have the picnic on the island. Okay. There's the domain. Circle crosses circle is the torus. Right? Do you see that? I mean, some of you are undergraduates. Do you see? At each point I have a circle. And then I want to find, if I had lines, coordinate system, I'd say here's where the x direction is the y, and I would write a lot of y directions in here. Here I have a circle, and I say, well, at each point on the circle, I put the other person's circle together. And I move it all the way around, and I move it across. And so therefore, the problem then, the decision problem is a mapping from the torus to a circle. Okay? All right. Question. What is going to be the good mapping method? Well, let's see. What are some of the properties we should have? We want to have minimal properties so that we can have the largest class of methods that would work.
She still talks to Bob.
Huh?
She still talks to Bob.
Number one, that they won't get a divorce. Okay. Well, you'll see that it's the other way around. We'll walk out to Sue. Okay. Property number one is that at least the mapping is continuous. You don't want to be over there on the beach and then Bob chooses, oh, about that much far off. You don't want the answer to jump all over the place. So you want the solution to be continuous. Second thing you want to have is unanimity. If Bob and Sue agree, then that should be where they meet. Third thing we should have is reasonable. If Sue wants to be here and Bob wants to be here, we don't want the outcome down here. In other words, if Sue wants to be here, Bob wants to be here, the outcome should be somewhere between the two. Okay? Everybody with me on that? And that seems to be enough properties to start. And so what's the conclusion? What kind of mapping do you think it has to be? Do you know the answer?
Map to one point?
No, he's saying a constant mapping. The answer is no, that won't be. It has to be homotopic to a function of one variable. What the hell does that mean? It has to be homotopic to a function of one variable. Stated in real world terms, it just says either Sue or Bob is dominant in making the decision. One of them decides and the other one can alter the decision a little bit. So what happens is you're Sue and I'm Bob. So you decide where it's going to be. And then I said, oh, I'm going to move it a little bit here to get out of the sun. Okay. And so, but you're going to be the dominant person in making the decision. Those are the only mappings that you can have. There's something of that type. So what you did is you decided there. That's your favorite choice. My favorite choice is there. And so therefore you said, well, let's meet there. You're a little bit compromising. It's not too much. But I can modify it a little bit to get a little bit more in the shade and get it there. Now, what does homotopic to a dictator? Because she's going to be the dictator. What does homotopic to the dictator mean? It means that we can take one of the two people, since she's the dominant person, you can take me, and you can continuously decrease the power I have until she has all the power. You like it? And so what we're doing is we can continuously decrease it until she has all the power. So it doesn't say that the rule is a dictatorship. It says that the rule can be continuously reformed into a dictatorship. But it says that one person must be dominant if you have a rule that satisfies these conditions. How do you prove this? You can prove this by use of algebraic topology, just simply looking at the indices of these in here, just comparing indices, etc. And you can prove it. I proved it by use of analysis. I first proved it by, and by that, I did that because I wanted to find how much these persons deviate from how much can Bob TV consumes. And in fact, as I said, a fairly easy proof is independence in both. Okay, yeah.
Among the maps that's homotopic, the function of one variable would be to always do the opposite of what person A wants. So why do you make the interpretation that means that person A has all of them?
No, actually, if you're opposite, the answer is that you won't have, you'll have zero color, zero input on it if you're opposite.
Isn't that homotopic?
Hmm.
In other words, if
No, I'm that the function is homotopic to a function of one variable. So what I'm doing is, I have, it's essentially a special case of that will be if I have your decision rule and my decision rule, and then what we do is 1 minus t plus t. When t is equal to 0, you're the dictator. When t is equal to 1, I'm the dictator, but so let's divide by over 2. So here we have a share, and there's by roll increases. And so that's what we have here. And so what we do is, this is the outcome. Now remember this theorem. Anybody have a question about this? It's a very simple theorem, but you're going to see it again. Okay. Now so these are very simple. This is if I have a torus, and the image is a circle, and that these simple conditions right here are satisfied, then the mapping has to be essentially one person has to be dominant in making the decision. The other person can have some voice, but not much. All right, let's go here. One of you just need a hole. Here I have a satellite going around the Earth. And there's a hole. We are not allowed to let the satellite go into the Earth. If you do, you have problems. Okay? Now suppose you're France and I'm the United States, and we both have a satellite up there, and we want to decide issues about it. And the question is that since there's a hole in the problem, there's a sphere, and it's got a hole inside, that the theorem is the same thing. That one person will be dominant in making decisions, and the other one can add. All right. Now, power of abstraction is that the same idea answers many different things. Let's go to this one right here. Now, I should have gone faster. This was another one. I should have gone fast and asked you for your connections. All right. Now, Nancy, you can help me with this. But somebody up in Canada went through and they were able to scale and find that emotions to be in a two-dimensional space, a circle with respect. You don't remember who. I know, a few thought maybe. Oh, that's serious. Okay. Okay, so what happens is that emotions can be almost a two-dimensional space, not a circle, but an annulus, really. But what am I using? I'm using tools of algebraic topology, aren't I? And in algebraic topology, I can contract this down to a circle. So the emotions are going to be, I can view them as being emotions on a circle. One side is happiness, the other side is sadness. One side is anger, one side is fear, and everything else. And they have it, and we go through it. It's UBC, somebody at UBC, psychology. I've got it in my notes at home. Okay, now each the eye is fascinating. In each eye, you've got one little receptor here that takes the images and puts it to the left side of the brain. And you've got another receptor that takes it and puts it to the right side of the brain. And it's in both eyes. Okay? So I got information coming from both sides of the brain. So what is it that we have? Well, each side is getting an image about the emotions because I have that split, face split, right? Right? Remember that? Face was split. So one side of the eye, if I do it fast enough, if I did it fast, we're going to do it slowly. One side is looking at one side of the image of the face. The other is looking at the other side. Where do the emotions come from? The emotions come from, so therefore it's a circle cross a circle. And we have to give an interpretation of an emotion. And what are the properties? Properties is that the mapping is continuous. If both sides of the face are the same, then there is no problem with the interpretation. if reasonableness, if a person is, one emotion is, the other emotion is like that. We don't want to have an emotion like that. So there has to be somewhere in between. These are all natural assumptions. And so what's the answer? You know the answer. The answer is that one side has to dominate. One side of the brain must dominate. That if you have the information going to the right side and the left side of the brain of this type right here, or it's split of this type right here, then it's impossible to construct a brain where you would always see the whole face, with the exception of you. Okay. Where you would see the whole face. That one side has to dominate in making the decision.
In your experiment, though, the decision had to be made extremely fast.
That's right, because we don't want the person to be able to see the whole face. That's exactly right. In fact, you got the next slide, that we're running a large number of experiments on this. And I got the theory done, and then the other two people are doing the experiments. And this is Kimberly Jameson and Louis Nerens. Now what we're doing is, all right, suppose we have one of these Photoshop pictures, the top and the bottom. Now if it's the top and the bottom, that's not going to give, the results we have here should be the same answer. And they don't. And what about the left and the right, and how far off? Remember I showed you that you could, when we decide where to have our party, what happens is she's dominant, but I have some leeway. And so we're running experiments to find out how much of a leeway can you have.
You get a bias in something like this where my mind is automatically processing text from left to right?
No. A lot of people do right to left. And in fact, one of the things which they're coming out is if you're left-handed or right-handed.
Okay.
But that's not a very strong correlation, but getting some information about that. So they're running experiments on you. But the point is the following, as far as mathematics is concerned. The point is that I showed you the picture. We have local data. And by stumbling on this result right here, I began to realize that, oh, it fits into this story right here. So I went with the lake party, beach party example to prove the theorem. But what you have is you now have a global story where we didn't have a global story before for those pictures. And we have an explanation for the phenomena that was said, well, look, we just have two sides of a brain, one side's going to dominate inside here. No, you can't construct a brain where both sides would be equal partners, is what it says. Okay? Now, let's go to this one right here. This one right here is a little bit more fun. Circles. Hue circle. You have a colored sphere. It's a sphere with a line going right the middle, right through the middle. But what we do is we have a hue circle where all the colors are. And so therefore, when the mind's looking at here, see now it's doing it slowly now, because you're looking at it. But the mind is doing what? It's slowly looking at that color and it's slowly looking at that color. And so it's slowly looking at something from a torus. And so, because this right here is going to be found in one direction of the torus, this is going to direction another direction of the torus, and that's going to interpret what's the color of the center. And so what we have then is what are the properties? This mapping has to be continuous. Unanimity, if this is all one color, you're not going to have any trouble. And reasonableness, that you don't jump in your interpretation. All of a sudden jump, that's something weird. And so what does this say? This says the conclusion that the mapping here must be homotopic to a function of one variable. That is, one color has to dominate in making the interpretation. That one of the colors, either the surround or the center, has to dominate in making the interpretation. And so again, the same group, Kimberly and Louis, are running experiments. And they pointed out to me that what happens is, which I don't know psychology, but they pointed out to me that intensity plays a role. There is another variable in here called intensity. That the intensity of which color is at the center or the surround that determines which one dominates in your interpretation of the color. that interpretation depends on which one is, if this is a kind of a light red rather than dark red. And so there I have a scalar. And so what the theorem that I then proved is that, well, at one situation, oneness dominates, at the other situation, the other dominates, and what happens in between? So what happens in between, I proved that there has to be a singularity, that it can't be continuous all the time. So I asked him, what's a singularity? He says, a gray spot. Don't you know what a singularity is? It's a gray spot. Oh, okay. And so then what we did is we jumped to the literature to find out, do they see gray spots? And indeed, as they change the intensities of the center and the surround, gray spots in your interpretation keep jumping up. In fact, there's a kind of a line of some of them. And so what happens here is, again, the theme that I'm trying to say is that mathematics, looking at these things, the mathematics that I'm using here, it's not easy, but it's not hard. And that the theme that we have here is that you get all of these, that you're able to get new insights and answer questions that have been around for a long time and create conceptual differences in what happens. And looking at the time, I was going to give one. I'll just quickly go through and give the last one. Any questions on this before I jump to the... Yeah, yes.
There's a phenomenon underwater where as you go down, colors are absorbed. First you lose red and then so you get down around 100 feet, everything is blue-green.
That's right.
But when you first start taking photography, if you don't use a flash, if the fish should be yellow, you will actually see a yellow fish.
Yeah.
And then you take the photograph of the yellow fish, and then when you look at it later, by cracky, it's blue-green.
That's right.
So is it because you have sort of the surface concept of dominance that you're, in other words, in making this decision, you're using just sort of your surface understanding as opposed to the actual color intensity you're getting?
You know, so what you're doing is a problem that we want to get to. We aren't there yet.
Okay.
We want to get to precisely that type of issue. And the Centersurround is the first step.
Okay.
But you're really in the direction where we want to get the answers. Hopefully you beat us.
Yes, photographs will get better.
Anyway, so now I'm going to skip Ptolemy. I was just going to talk about Ptolemy and show you more things about the circle. But let's but the U.S. apportion. Now, just let me give you why there are 435 representatives in the U.S. Congress. Okay. Let's suppose I'm just going to have 3 states, only 3 states, and I'm going to try to add them together. And I just chose numbers at random. And these randomly selected numbers come to a population of 10,000. So state A has 4,290, B, et cetera, et cetera. And so therefore, state A has, 10,000, just so conveniently it comes out that state A has its fraction of the total number of representatives, et cetera. Just look at this. Okay, now suppose I have a house size of 10. And the question is how many representatives should each state have? And the idea I'm going to show you is the idea that came from Alexander Hamilton. And it led to the first presidential veto ever by George Washington. Okay, talk about political science. Okay, now what they did is with house size 10, what happens is, well, multiply 10 times this, and A should get 4.29 representatives, B should get 4.3, and C should get 1.41 representatives. And they were not into giving portions of representatives out, okay, for obvious reasons. So what they did, Hamilton's idea was, look, let's take the integer amount. Now, we have 9, so I have 1 left over. So who should get the extra representative? Well, let's look at the fractional part to see who's got the largest fraction. And that is C. And so there's our portion. 4, 4, 2, 10. Okay, everybody see that? Pretty simple. I mean, let's just be sure. Let's do it one more time. Let's do it for 11. So I multiply 11 times this number, I get this. 11, 11, I get that. And so now when I take a look at the integer part, it's 4, 4, 1, so I get 9. Now I have 2 left over, so I look at to see who has the largest fraction. 7, 7, 6. Oh, damn. C got Alabama. Okay. C got Alabama. C had 2 here, increase the size, and you get 1. All right. This caused an uproar. I just loved some of the literature where Congressman so-and-so says, God save the United States from the gods of mathematics. Okay. All right. And in fact, in 1910, they raised, for the current population of 1910, they raised the number of representatives in the House of Representatives to avoid a paradox where somebody gets hurt. And that number was 433. And there were 2 territories, Arizona and New Mexico. So they saved a representative for each of those, and we got 435. So therefore, 435 representatives is the consequence of a mathematical paradox. I love that. Okay. Now, where does it crop up? It's got to have a torus. So let me show you a torus. So if I'm rounding off, if I have that point and that point rounding off, they round off the same. In other words, when I'm looking at the rounding off numbers, I'm looking at just an interval where the endpoints can be equated and they can be turned into a circle. So when I'm looking at Hamilton's method, I'm really looking at rounding off as a motion on a circle. As I'm moving along here, it's 0, I get to a certain point, it jumps to 1. I get back to this point over here, et cetera, et cetera. So it's a motion on a circle. And I got 50 states, I got a 50-dimensional torus. Try to explain that to a congressman. I made a mistake and tried it once. And what happens then is the apportionment problem is a decision problem on a 50-dimensional torus. Now, there's a couple of you who looked at flows of circles and torides and things like this, and so you know that all kinds of mess can crop up there. And so the theorem that I do is that once there's 3 or more states with probability 1, an apportionment will yield an Alabama paradox for some both sides. It can't avoid it. It's because of the structure of a torus. Is that where you're getting this? See, again, celestial mechanics plugs in here. Okay? And so this is what we have. So really what I wanted to do is the following. I wanted to give you a flavor of several types of problems that crop up in the social sciences. We started with a voting problem. We then looked at a couple problems from psychology, behavioral sciences. We looked at an apportionment problem. All of them extend in many different directions. And I wanted to give you a flavor of at least how some of the answers are coming in these areas. And the answers are coming from mathematics by looking at what is the structure and then trying to figure out what's happening. This is just a flavor of the kinds of mathematical social science problems. And let me tell you, there's many, many, many more fascinating problems. Steve was out at the IMBS, and I think he will agree that if the question is not, can you find a fascinating problem that needs mathematics to try to give some insight, the question is, how can I narrow it down to a lifetime of problems where we can make these? And so really what I'm doing here is there's fascinating problems. It's an opportunity to change the conceptual way in which a field looks at itself. And so I'm inviting you to join us in examining these issues. They can be fun. And with that, I just say thank you very much.
Are there more questions, comments?
Any questions, anyone? Yeah.
I didn't really understand with the very first beach problem, the picnic on a beach. You explained how you're mapping from a torus to a circle, and you said that 1 always has to be dominant. Why couldn't you just have the map where you choose the halfway point?
Ah, excellent point. Oh, God, that's excellent. Because you see, she's saying that suppose we're on a beach and I'm not on a circular beach. We can just do what? We can just take the average.
Well, even on the arc, can't you just take the halfway point?
But suppose you're now, suppose you're opposite, exactly opposite each other now.
I see.
And now when you're exactly opposite, now you're running into a difficulty, aren't you? And if I take a point on the interior, if I move it a little bit, now I can jump over here. And no longer is continuity. Excellent, excellent question. So what she's saying is, see the structure of the domain plays a big role. What she's saying is, why don't I just take the average? Don't take 2 points and take the average point in between. You know, what's wrong with that? And so the answer is that you can't do it. Suppose you're on the opposite right here, and I take the average, I'm right here. Okay? Now I move this a little bit, continuity, now it's going to jump over here. And it loses continuity. And the amazing thing is that the brain doesn't know the mathematical theorem, but it behaves accordingly. Unless you get to some of the other type things where things jump up the actual boundaries. But it just does that. And the same thing is true with satellites. Okay? And so what you're doing is that one person has to be a dictator, but you're saying that I can have any point I want in the interior, but as this point gets closer and closer to here, I better be closer and closer to that point. Very, very close to that point. Because I don't know when that's going to jump, it's going to happen. And so therefore, it shows you where the dominant is the contributor. Good question. Any others? Any other questions? Oh, I lose you.
Thank you.